Hello, how are you? My name is Juan Camilo Rivera, and today we're going to talk about two different methods, PCA and tSNE. So let's begin with PCA. These are the principal component analysis. And what we want to do is to reduce the dimensions of data. Why? Because when we reduce the dimensions, we are going to have a better efficiency for processing. We are going to have a better interpretation of the results so that we can take better decisions on what model or what objective we want to reach. So mathematically speaking, what we have is p variables, p dimensions, and what we want to do is to reduce them to an n that's below p, so that it's a good abstraction of the information that we had originally. In the right part of your screen, there's an example. It's an analogy. And right here, we can see a system that has a particle in spring. And we do the analogy, take into account that Pca works as if we had three cameras aiming at the system. So Pca, what this does is to take a picture by those cameras that we have, so that all the information of the spring particle is going to be compiled in these pictures. In R, we're going to learn how to plot this graph that I'm aiming at with the pointer. This graph, before explaining it, I would like to tell you how a PCA works mathematically speaking without going into details on values and others. So geometrically speaking, what we're doing is taking the points, in this case, these are the red points, and we are projecting them on a plane. So this is the main component. What we do is to get a point and project it. So we're going to project each one of those points. And the other component is going to be orthogonal to this first component. We're going to project them also. The fact that these are orthogonal, they guarantee that they're independent. So once we understand how the PCAs work, we start to do the PCA plots. There's a range that goes to -1 to 1 in the axles. This means that this is there's a coefficient, a correlation. So for example, we get this yield, we can see that in the second dimension, it, it gives us 0.25. And that accumulated precipitation is of 0.75. So there's a relationship between the second dimension and the first component, but there's a low correlation, as also the accumulated radiation. What helps us to understand this graphic? Right here we can see how much each variable gives for each dimension, and we can also see what's the relationship, if these are direct relationships between the variables or inverse relationships. If there's a 90-degree angle between the variables, we can see that there's an inverse relation. So for example, accumulated rain has an inverse relation with yield. Instead, yield and solar radiation, this would be direct. This is PCA. Now we're going to see how it's implemented. The second method is tSNE. That's also to reduce the dimension, and it's also used to visualize. This method is created from nonlinear methods that allow to assign probabilities in high dimensions to certain points, and then the stochastic processes are used to use that representation. I like this graph that shows a map of the world where the representation is done in 3D, and then it shows these two other methods and how they look like. So we can see that in this case, in the example of the 3D map, we can see that Pca and tSNE have a very similar representation. However, it not always happens this way. Some methods work better with Pca, others with tSNE. So it depends on the context of the problem. In Pca, in the next video, we're going to see what's that parameter that we're going to use and what results it's going to give us. That was all with Pca and tSNE.